Hey everyone, my name is John Pagliata from Vector America, and I'm going to talk to you today about a little bit of history. I'm going to talk about a guy named Edwards Deming and his impact on manufacturing quality, and then some ideas of how we can apply that also to software quality. So who was Edwards Deming? Edwards Deming was basically a management consultant who did a lot of work with the Japanese manufacturers in the 1950s. And he had some core beliefs. He thought that if we improved quality, we'd also reduce cost. And then having an improved quality and lower cost would make the Japanese products more popular. And also you'd build customer loyalty. And if any of you are old enough to remember the 70s and 80s, you might remember that the products held in high esteem at that time for quality were those from Sony and Toyota and Honda. So he was largely successful. So how did Deming change manufacturing? Well, basically, before Deming, everything was done as an independent step. So you'd have the designers who didn't talk to the people who were designing the factory. The people running the factory didn't talk to the people who designed the factory, and the people testing the product at the end didn't really talk to anybody else. So you would get products coming off the assembly line, and they'd be tested for their final acceptance test. And then some of them passed and some of them failed, and they'd have a big pile of failed ones, and they take those off and diagnose what was wrong with them and try to fix them. So that seems a little crazy now looking back on it, but that's how things worked. And so his idea was we needed everyone to be integrated, working, pulling on the same oar, working in the same way to improve quality. And most importantly, we needed to measure quality at each step. And then when something failed, not just fix it, but find out maybe why it failed in the first place and improve that part of the process. So let's look at how some of these same ideas can be applied to software. So if you look at the software development process, we basically have people who do the design, the code, and then the integration testing, and then the final QA testing. And to me, the biggest problem with this is generally each of those groups has their own set of test cases. And many times the groups don't have access to each other's tests. So we certainly have independent processes as Deming would have described them. So we've got the designers, the developers, and the testers working separately, each running different tests. And then what is the result of this? The result is, when we're trying to ship, the final arbiter of whether the product is finished or defect-free is the QA group who are running these hill tests. And so a lot of times, the first time these tests are run by anyone is once the product's been integrated, and then they pass back bugs that they find to the developers. And so the developers, in a sense, are being tested against some criteria that they've never seen before, because the final acceptance tests weren't available to them for dry running before they integrated their stuff. So how could we improve this? Well, to me, the best way we could improve this is come up with an integrated test suite that everybody contributes to. So the developers send their unit tests to the common test suite, the integrators send the SIL tests, the system testers or QA group sends in the hill tests. And then most importantly, this has to be a continuous and automated process so that everyone on the team can contribute tests, but they also can use the tests. And then the other part of this, right, from Deming is that we need to prevent bugs by improving the process to make things better. So the best way to do that is to record key metrics from each stage of the process. And then rather than QA being the arbiter of when we ship by whether their tests pass, the metrics dashboard should tell us when to ship, because it should be an objective measure of quality that everyone has contributed to. So let's dig into how we can have integrated test processes, continuous testing, and bug prevention as it applies to software. So how can we build in quality? Well, there are 3 steps for this. One is to test each component before we integrate it. The next is to build tests based on the APIs and the requirements, not based on the implementation. And then the final step is to ensure our testing is complete, and code coverage is a great way to ensure testing completeness. So what do I mean when I say testing a component in isolation? What I mean is first defining a component logically. So a component is not necessarily a function or a file or a set of files. It'll vary depending on what the application does and the parts of the application do. So the component should be defined logically. Oftentimes, unit testing gets a bad gives people a bad impression because they spend a lot of effort on it and they don't find a lot of the bugs that they expect to find. And I think that's often because they define a component too narrowly. It can't always be a file or a function. And then you need to expose the tests that you're going to use for this API or component testing to all stakeholders. So you shouldn't have just unit or just SIL or just hill tests, but we should just have a pool of tests, as I showed in one of the slide a couple minutes ago. And then all of them, most importantly, need to be runnable by all stakeholders. And then finally, let's refactor test cases over time. How many of you throw away obsolete tests? I mean, usually out of fear, we very seldomly delete a test because we're afraid of what it was testing. And so that's not the right approach to having a very good independent test process. So let's talk about building tests for APIs and requirements. First, I'd like to ask you where you find more bugs. Do you find more bugs unit testing or during your hill final QA testing? Probably the more serious bugs show up during hill testing because then all of the components are working together and you're going to identify maybe errors that were made in the implementation of one component or another. So in the same way, when you're designing test cases, it's important to think ahead of how the component's going to be used, not how it was implemented. So oftentimes, if we build test cases with the implementation in mind, we're going to make the same mistakes when building the test cases that we made when we did the implementation. And so I often tell people the way to think of this is when you look at an API, think of how can this API be used. So, the silly example is if you have a function foo and it takes an integer, someone could call that with -2 billion, right? Now you'll say, well, nobody should call it. Of course they shouldn't call it, but what do you do if they do call you with -2 billion, for example, if you have an integer? The other benefit of thinking about requirements and requirements traceability while you're doing this testing is anytime a requirement changes, you have a way to track the fact that you should look at code changes and test changes. So requirement changes imply code changes, and if you're really diligent about it, the code shouldn't be changing without a requirement changing or a bug. The final step to building in quality is to measure testing completeness. And in my mind, the best measure of testing completeness is code coverage. I think the mistake people sometimes make with code coverage is to assume that 100% coverage is the goal, and that's not the goal. Code coverage is just a measurement of testing completeness. So the goal really should be to run all of your tests and then measure the coverage, and then not just create test cases to fill in the missing coverage, but think about why you don't have API and requirements-based tests that provide 100% coverage. So maybe you missed a requirement, maybe the implementation doesn't match the requirement. So somebody put an extra case in a case statement when the requirement said you had 3 colors, red, green, and blue, and then they actually implemented tests for violet or something like that. So the process for using code coverage should be iterative. You should write the tests, measure code coverage, and then investigate the root cause of the lack of 100% code coverage. Okay, now let's talk about how to make testing continuous. So there are 3 components to this also. First, make it easy. So people will do what is easy. So make it easy to build tests, understand test results, and debug failing tests. Make it fast. Nobody hates anything more than sending off their tests to be run and then finding out 3 days later that there is a test failure. And then make the test execution automated. Should be push button. Anybody should be able to run the test. They shouldn't have to worry about whether they have the right tools installed, what the manual setup steps are, or anything like that. So how can we make testing easy? They must be shareable. So there can't be separate flavors of tests that are owned by separate groups like I showed in one of the initial slides. Everybody has something to contribute, so let's use people's abilities to contribute what their knowledge of the system is. They must be small and easy to run. So anybody has to be able to run any test at any time. And then it must be really simple, pass or fail, not parsing manually or with tools through long log files to figure out if something passed or failed. And then finally, please, for the sake of your developers, make tests debuggable. So if you give me a test that fails in the application in a debugger, you're going to get a fix really quickly. The next step in continuous testing is to make testing fast. So why is testing slow? In general, testing is slow because we all have hundreds, if not thousands, of test cases, and understanding which test cases should be run for which source changes is a very difficult problem. So out of an abundance of caution, we generally run all of our test cases, and if that takes 3 days, you end up with developers having to go off and do something else while they're waiting for the results of their testing. And so that leads to a lot of inefficiency because the developers context switching away from what they were doing and back to what they were doing after they have a test failure. So what we're looking for with change-based testing is running only a subset of test cases for each incremental source change. And so by using code coverage, we can intelligently understand which parts of the application are stimulated by each test, and then we can map that back to code changes and then suggest to you that this subset of test cases should be run based on the code you've just changed. Now, we're not suggesting that you would release by running only a subset of test cases, but we are suggesting for the day-to-day work of the developers, they can get much faster feedback loops if you're running only a subset of test cases that are actually most likely to fail based on the changes that have been made. And the final step to continuous testing is to make testing automated. It's amazing to me how often I talk to customers and they have some portions of their testing, or maybe a large portion of their testing, that involves manual setup or manual tests. We have to filter this out of your test environments. It just makes no sense, and it doesn't make testing and doesn't make it easy for people to do testing. And if it's, as I said earlier, if it's not easy, people are not going to do it. So we also need to remove infrastructure limitations. I think people, especially with embedded projects, often have limited resources as far as demo boards that they can actually run their application on. So there are a few different approaches there. You can even either have virtualized test environments or in some way build a custom simulation environment that allows your embedded application to run in a native environment. And then it has to be push button. There can't be this complex process of pre-test setup and post-test evaluation of pass-fail. It has to be simple, push a button, pass, fail, and an easy way to debug if a test fails. And the third part of Deming is determining the root cause of failures and improving the process. So how can we do this with software? Well, ideally, you want to prevent bugs. And so there are three components to preventing bugs. One is to identify the quality metrics for your project that really drive quality. The next is to analyze data. All of us on our projects have plenty of data, but what is it telling us? And then finally, using the data that we extract from our software development process to improve the process itself. There are a lot of different metrics you can capture, hundreds of different metrics, and I'm obviously not going to go through a lot of them, but I'm going to put up just a few that I think are important. Logic complexity, this has been around forever, cyclomatic complexity, but it's still a good indication of the maintainability of the code. How many unique paths exist through the code? Interface complexity is often overlooked. How many inputs exist for each function? If I have 5 structures with 100 fields in each one, probably a little too complex. Maybe that should be flattened down into a flat list of 5 or 6 scalar values that are really used. Comment density. I'm a massive believer in the value of comments and maintaining comments. Frequency of source code changes. With the modern tools like GitLab and GitHub, it's very easy to draw yourself sort of a heat map of what parts of the code are changing most often. Those either indicate a lot of new features are being added or maybe a lot of bugs are being fixed. And then finally, testing completeness, getting back to code coverage being a great great metric for understanding how complete your testing is, if, as I said earlier, it's used the right way. So once you have the metrics, what do you do with them? Well, it's important to analyze them and then set some goals. So it's sort of irrelevant what your starting point is. So you might start using a static analysis tool and have 500 findings. Well, sure, you spin through them and find the most important ones, and maybe you fix those right away. Or you might measure code coverage for the first time during your system testing and find that you're at 50 or 60% code coverage. The point is not where you're at. The point is incremental improvement, as Deming said. So let's measure metrics. Let's start tracking progress with these metrics. So if you choose goals, so you want cyclomatic complexity to never be higher than 10 or 12 or something like that, let's start checking that for all of our new code. Don't allow a commit if the cyclomatic complexity of the function is higher than 10 or 12. Let's not allow a commit if we don't have tests to show, demonstrate 100% code coverage of the changed code, things like that. So trends are the key. It doesn't matter where you are. It does matter that you have a goal of improving, and it does matter that you have an automated way to measure where you're at and how you're changing over time. So the final step in bug prevention is to implement quality gates. So without gates on behavior, your code base can become really ugly really quickly. So once you've determined the metrics that you're going to record, you've come up with some goals, some targets for those metrics, then you need to implement automatic gates so that someone can't commit or certainly not integrate something that doesn't meet the targets you've set. So if you decide that you're going to have complexity less than 10, then we don't allow a commit unless we do an automated check of the complexity on the code being committed and ensure it's less than 10. Peer review is an obvious one that we've all done forever, but how about code coverage on changed code, or test case to requirement mapping document being updated? And clearly all tests must pass. And that's the most important one, because what all tests mean has to be the same for everybody on the project, as I said up front. So with too many gates, nothing gets done. But if you have documented and automated workflows, then people will adjust their behavior to fit the workflow that you design, and you'll get much better quality out of the process. So final thoughts. If we have an integrated test process, then we're going to build in quality, as Deming had in mind. And if we have continuous testing, then we're going to be able to measure quality at each step in the process. And then finally, if we measure metrics and have goals, then we're going to improve the process and prevent bugs before they're introduced. Thanks for listening today, and I'd be very happy to answer any questions you might have.